Mm. So today we will be hearing from Houraa. She is a fifth-year PhD candidate in ocean sciences working in Ben Kirtman's lab. She graduated with honors from the University of Michigan in 2015 with a BSc in Earth System Science and Engineering. And she has conducted research with NOAA's Great Lakes Environmental Research Lab and at NASA's Goddard Space Flight Center. She's gone and done field work in the Agulhas system and here locally in the Florida Straits, and has even volunteered with the Adidas undergraduate cruises, where she helped to educate students on oceanographic techniques and methods last spring, right before the Great Quarantine started. And so today we will be hearing Houraa talk about the Southern Hemispheric response to ozone recovery.
Thank you for that introduction, Casey. I will share my screen with everyone. Okay. I just want to start my timer. So as Casey said, I'll be talking about the Southern Hemispheric response to ozone recovery. This is a project that Ben and I started in the last year or so. And as always, all feedback and suggestions are welcome. So I just want to begin with a little illustration that we created comparing the ozone depletion to the ozone recovery. And so on the left, we have the ozone depletion, and on the right is the ozone recovery. Beginning with the ozone depletion, with anthropogenic climate change, we've seen the ozone layer thinning, or depleting as they say, and that causes a cooling in the lower stratosphere and a warming in the troposphere. This warming then leads to an increase in the height of the tropopause, which causes a poleward shift. So here we have the poles of the westerly jet, the Hadley cell, the storm tracks. So you're getting more precipitation at high latitudes and less precipitation now at the mid latitudes. The ozone depletion time period also leads to an increase in sea surface temperatures and a decrease in the sea ice. So you have an increase in sea ice melting. Another thing that's not marked on here that I want to talk about is the Southern Annual Mode, or the SAM as it's known. And that is the leading mode of variability in the Southern Hemisphere. And so in the ozone depletion time period, it's in its positive phase. So you get higher than normal pressures over the mid latitudes than you do at the high latitudes. And this causes the SAM to be in its positive phase. And then if we switch looking at the ozone recovery time period, so with the implementation of the Montreal Protocol in the late 1980s, there was the banning of the ozone depleting substances. So you get a reversal or weakening of all the trends or shifts that we saw in the ozone depletion time period. So that means a decrease in the height of the tropopause, an equatorward shift in the westerly jet and Hadley cell, and then back to an equatorward shift of the storm track. So you get the return of the precipitation at the mid latitudes. Although you're still going to see an increase in sea surface temperatures, they're not going to be as drastic, and then there'll still be sea ice melt, but again, not as drastic, which is shown here. And then going back to the SAM now, we get higher than normal pressures at the high latitudes now, causing the SAM to be in its negative phase. So that's something that we're going to talk about throughout this talk. So it's been shown that the ozone depletion plays a large role in the Southern Hemisphere climate. And so here are just some previous studies that basically reiterate what I said previously. So we get a poleward shift or expansion of the westerly jet, a poleward shift of the edge of the Hadley circulation, poleward shift in the subtropical dry zones and storm tracks. We get a change in the wind-driven oceanic circulation, as well as changes in sea surface temperatures and the extent of the sea ice. And then as mentioned, with the implementation of the Montreal Protocol, we can expect the recovery of the ozone by the mid-century. This recovery will then lead to the weakening or reversal of the ozone depletion trends. And during the ozone depletion time period, we have ozone and greenhouse gas forces working together. But with the ozone recovery, these two forces will begin to oppose each other and essentially cancel each other out. But how these trends continue after the ozone recovery will depend on the greenhouse gas emissions. And that's something that we'll look forward we'll look at going forward in this study. So the model used is the Community Climate System Model version 4, CCSM4. The atmospheric model is CAM. It is 26 layers at 1 degree resolution. The ocean model is the Parallel Ocean Program at 60 layers at 1 degree resolution as well. So this is the low resolution version of CCSM4. The ozone in these simulations are calculated offline using interactive chemistry. So it uses the chemistry model of the atmospheric model. And then there are monthly mean outputs. So that's what we're going to use in this study. These simulations were run as part of the Coupled Model Intercomparison Project Phase 5, so CMIP 5. This is different from CMIP 3 in that there's actually a time-dependent ozone prescribed rather than the fixed ozone in CMIP 3. So we'll have changing ozone and greenhouse gases simultaneously. Forcing used in this study is the historical and 3 representative concentration pathways, RCPs as they're known. With 5 ensemble members for each one. And so the historical is any time period before 2006. So in this run, it'll be 1970 to 2006. And the forcing during this time period is the 20th century CO2 level emissions. Then we consider RCP 2.6, which will be shown in blue throughout the talk, RCP 4.5, which will be shown in green, and RCP 8.5, which will be shown in red. And so these numbers at the end, 2.6, 4.5, and 8.5 correspond to the emissions level seen at the end of the century. We take 3 different emissions scenarios, so 3 different RCPs, and model what Barnes et al. Did in 2014. We take 3 because there's no independent, because the ozone isn't prescribed independently, we can't see the effect it's having, but we can extract the ozone fingerprint between each RCP scenario. So any signal that we see show up in all 3 RCPs, we attribute to being a response to the ozone. And that's similar to what Barnes did. And then continue to follow what they did. We split into 3 different time periods. We have the ozone depletion time period, marked from 1970 to 2005, the ozone recovery time period beginning in 2006. And like I said, the ozone's expected to recover by the mid-century, so to 2045. And then our post-ozone recovery period is going to be from 2046 to 2100. So if we update the illustration shown at the beginning now to include a post-ozone recovery panel, I've added in the years at the bottom so you can see 1970, 2005, 2006 to 2045, and then for the post-ozone recovery, 2046 to 2100. And so we have these 3 different RCPs, again, color-coded so you can see how it's going to be shown throughout the talk. So RCP 2.6 is our low-level emissions. So into the post-ozone recovery, you're going to expect the ozone force to continue to dominate and see results similar to this ozone recovery period. For 4.5, shown in green, the ozone and greenhouse gases are going to be almost equal and tend to cancel each other out. So we might get patterns from ozone recovery, and we might get some from the ozone depletion. And then lastly, our high emission scenario, so RCP 8.5 shown in red, the greenhouse gases are going to dominate during this time period, and you're going to expect to see results similar to the ozone depletion time period. So some things that are consistent throughout the talk that I'd like to note, we take the 5-member ensemble mean for each RCP to get rid of some of the interannual variability. We use the austral summer means, December, January, February. There's been shown to have the ozone forcing has a seasonal cycle with the stratospheric cooling shown in austral spring, so September, October, November. And then the time for the stratospheric signal to reach the lower stratosphere or lower troposphere is lagged. So that's why we look at the December, January, February means. That's where we have the largest signal. And then we smooth our time series using a 10-year moving average filter. We don't get any sort of change in the trends by doing this. It just makes the time series look a little nicer. So that's why we do that. And then all the trends in linear regression maps are calculated using linear least squares regression. And then all the significance that we show is within the 95% confidence interval and marked with an asterisk. So just a I just want to show the forcing used in each RCP scenarios and how they differ, and as well as explain the setup for each of my time series. So the ozone depletion time period is going to be marked by this dashed line here in this first box. The ozone recovery is right here in the middle. And then the post-ozone recovery is this last box, essentially. And so the historical is shown in black. And for that time period, we're going to get the same results regardless of RCPs, because that's pre-2006. And that's the historical forcing. So all the trends that we see in this time period are the same. And then you can see RCP 2.6 shown in blue, RCP 4.5 in green, and 8.5 in red. And as I mentioned previously, the values that are at 2100 are corresponding to those numbers there. So 8.5, 4.5, and 2.6. So RCP 2.6 is the extreme mitigation scenario. We have its peak around 3 meters here, and then it begins to, or 3 meters per watts per meter, and then it decreased down to 2.6 watts per meter squared at the end. And then for the 4.5, that's our stabilized one. So by 2070, you get it at its peak, and then it stabilizes the rest of the century. And 8.5, you get a continued increase throughout time. So this is the worst case scenario, continued emissions scenario. Yeah, and then looking at the CO2, it shows the same trends, but I just want to show it as another variable so that way you could see what it looks like in terms of CO2. And we're around 400, 450 right now. And so you can see if we want to reach this 2.6, we need to stop all net emissions essentially. And then for 8.5, that's again, worst case scenario, continued burning of fossil fuels and highest emission scenario. And so this bottom figure shows the stratospheric ozone in the Southern Hemisphere for September, October, November. And you can see that it depletes by 2005. So this is our ozone depletion time period where you get a really strong decrease. And then you get the start of the ozone recovery seen here. And then by the end of the century, you're at levels seen back in 1970 when it was recovered. Or healed, I guess is how you'd say it. So this is when we'd expect our full healing. And again, we consider 3 different RCPs for a few reasons. One, so that way we can extract the ozone signal, but also because we don't know what the future lies, this kind of serves as a future projection. And by considering 3 different emission scenarios, we get 3 different storylines of what could happen. So I'll begin with the westerly jet in the Southern Hemisphere, which is defined as the maximum wind at 850 millibars. And again, all trends with significance are marked with an asterisk. And then each trend is color coded for that time period. And so beginning for the historical ozone depletion time period, for the maximum strength of the westerlies, we see there is an intensification of the westerlies, which is consistent with previous literature. And then as we move into the ozone recovery, we should expect either a weakening or reversal of the trend. And so for RCP 2.6 in blue and 4.5 in red, we actually get a reversal of the sign. So they are slowing down. And then for 8.5, there's a weakening. So you can see the effect the ozone recovery is having on the westerly strength. And then as we move to the post-ozone recovery for 2.6, it's a continued weakening of the winds, a decrease in the intensity with the negative sign. And then for 4.5, it's close to 0. So it's almost a stabilization that we're seeing there, consistent with the greenhouse gas emissions for that time period. And then lastly, for 8.5, beginning in about 2060, you see this very strong increase in the intensity of the winds, suggesting that the greenhouse gases are reverting back to trends seen during the ozone depletion time period, and we're getting a strong intensification of the winds during this time. Next, we look at the latitude of the westerly jet, and so this has been shown in previous literature as well. And this is the one where we're getting the strongest signal. You can see that all of our trends are significant. And so beginning with the ozone depletion, we get a strong decrease or so a poleward shift of the westerly jet. And so it's about 1 degree shift over this 35-year time period. And then as we go forward for the ozone recovery, there's not a change in the sign, but there is a weakening of the trend across all 3 RCPs. And then when we go to the post-ozone recovery, RCP 2.6, begins its equatorward trend. So that's what we showed in the beginning, where you're expecting the westerly jet to shift back towards the equator. And 8.5, however, again, in this around 2060s, where you start to see this big change, you get a really strong poleward trend that's on par with the same value and trend that we find for the ozone depletion time period. So we get this very strong poleward shift in the westerly jet. So we compare this with what was found in Barnes et al. I just want to make a quick note that Barnes considers all the models used in the CMIP-5 simulation. So it ends up being about 30 different models. And then if we compare values, we are underestimating the trends compared to Barnes by more than an order of magnitude. But if we're just looking at poleward versus equatorward shift, we can find that we are in agreement. So for the historical time period, we get a poleward shift in agreement with Barnes. And then for RCP 2.6 ozone recovery, a weakening of the trend, but still poleward. And then post-ozone recovery, we get a reversal of the trend, and it's moving towards the equator now. And then we get the same thing for 4.5, where we both get a weakening of the trend throughout time, but still slightly poleward. And then lastly, 8.5, we have the slight weakening for the ozone recovery period. And then the post-ozone recovery period, we get a strong poleward shift, indicating that the greenhouse gases are more dominant during this time and causing that poleward shift. Next, we look at the Hadley cell. So the Hadley cell is the zonal mean of the meridional mass stream function, and its edge is defined as the latitude where the stream function is equal to 0 at 500 millibars. And so we get trends similar to what was shown in Barnes et al. And with the westerly jet. And so we get this strong poleward shift of the edge of the Hadley cell seen here in the ozone depletion time period. As we move to the ozone recovery, RCP 2.6 switches signs and begins its equatorward shift. And then RCP 2.6 or 4.5 and 8.5 weaken as well. And then moving on to the post-ozone recovery, we get a continued decrease or equatorward trend of RCP 2.6. And then for 8.5, the same thing that we've seen before, starting around 2060, a strong poleward trend seen here again. And so that's been consistent with previous literature and what we expected. And so we compare this result of the westerly jet versus the Hadley cell relationship with what was shown in Polvani et al. So they look at the latitude of the jet max at 850 hectopascals and the latitude of the Hadley cell edge on the y-axis. And so they look at a couple different emission scenarios. The one that's similar to ours are these green dots here. And you can see that in their high resolution model, they are getting a much wider range or a larger shift in latitudes than we do in our model. So we're probably still underestimating the actual shift that's happening. But they get a correlation coefficient of 0.93. And so to read ours, we consider the black with the blue, so historical with RCP 2.6 as the 2.6 time series, black with green for the 4.5, and black with the red for the 8.5. And we get correlations of 0.77, 0.87, and 0.93 in agreement with what Polvani find. So as the westerly jet is shifting forward, the Hadley cell is as well, and vice versa. So next I'm going to explain a few different maps that we looked at. And so on the first row, we have RCP 2.6. The second one is 4.5. The third one is 8.5. And then the first column is the ozone recovery time period minus the ozone depletion. And then the second column is the post-ozone recovery minus ozone recovery. So these are difference maps. And so we're going to start by looking at the sea level pressure. And so this is where I mentioned that any signal that we extract or that we see in each of the three RCPs, we can attribute to the ozone recovery. So in this one, for example, you're seeing a decrease over Antarctica surrounded by this increase. And so the sea level pressure, the signal is really small. And this is, I just want to show it to touch on the SAM that I mentioned earlier. So the SAM is defined as the sea level pressure difference between 45 south and 60 south. And so when looking at it in this model, we found that there is a positive phase for the ozone depletion followed by a negative phase for the ozone recovery. But it was very weak. And so we're not getting a really strong SAM signal from the sea level pressure in this model, which I think has been shown in previous studies as well. So this model doesn't do a good job of capturing the SAM. As we move to the post-ozone recovery to the ozone recovery, or post-ozone recovery minus ozone recovery, we can see for RCP 2.6, we're getting a reversal of the trend seen here with a decrease in pressure on the outskirts and an increase over Antarctica. But I want to draw the attention down to 8.5, where we get a really intense signal seen as a result of the greenhouse gases. And places where we see decreases in pressure are Eastern South Africa, Australia, and Western South America, which I'll be touching on in a second. Next, we look at the sea surface temperature. So this is not an exciting figure to look at. As you can see, there's warming everywhere, but the sea surface temperatures do play a large role in the study, which is why I wanted to talk about it. So for the ozone recovery minus ozone depletion, we get a warming that's similar across all three RCPs in about 1 degree warming of the oceans. You can see there's a little bit more intense warming around the ACC. But that's pretty much it for the ozone recovery minus ozone depletion time period. But as we look at the post-ozone recovery minus ozone recovery, we can see the role that the greenhouse gases play here, with almost no change in the RCP 2.6 scenario. So we're getting very little change, about 1/4 of a degree. A similar response for 4.5 that we saw previously, about 1 degree, and then a very intense warming seen for RCP 8.5 of about 2 to 3 degrees. So you can see that the greenhouse gases are really going to dictate what happens in the oceans as we move forward past the ozone recovery time period. So next we consider latent heat. These warmer waters that we see from sea surface temperature increase are associated with an increase in latent heat as well, which is important for rainfall. With latent heat, with an increase in the latent heat fluxes, there's an increase in convective cloud formation and moisture content, and that leads to the advection of the moisture over land, which leads to an increased rainfall. And so that's why we tie latent heat, rainfall, and sea surface temperature together in this study. And areas where you really see this, and there's a strong increase in latent heat fluxes, are western boundary currents. So that's going to be another focus that we look at. And so the overall trend, although there are some regions that are decreasing in latent heat flux, is a warming. So we get an increase in the latent heat. Places where we get a decrease, you can see are in Eastern South America and Western South Africa. And so again, moving on to the post-ozone recovery minus ozone recovery, there's not much change for the RCP 2.6 scenario, a similar change for 4.5, and a very intense change for 8.5. And you can see these areas I talked about where we get a decrease, and then a strong increase over land on Australia, Eastern South Africa, and Western South America. So lastly, the last map I want to show is the convective precipitation map. And so in all of them, we get a really strong increase in equatorial rainfall, as well as an increase over Eastern South America or Western South America and Eastern South Africa for the ozone recovery minus ozone depletion. And we get a decrease over the Atlantic and in Western South Africa. And so for the post-ozone recovery, we continue to get an increased precipitation in the equator, as well as in 4.5. And then looking at 8.5, this is where we see the most intense change once more, with really strong increases over Australia, around the equator, Western South America, and Eastern South Africa. And then a decrease over the Pacific over here, and Eastern South America and Western South Africa. And so we choose to look at convective precipitation because these are related to the latent heat fluxes and sea surface temperatures as mentioned previously. And so the next thing I want to focus on is this area right here in Southern Africa. So this dipole pattern that we're getting over South Africa, where we have an increased rainfall in the east and a decrease in the west. So why I chose to focus on South African rainfall, it's home to a significant rural population that is dependent on rain-fed agriculture. South Africa is prone to large-scale flooding and drought events. I'm sure everyone remembers in 2018, Cape Town was one of the first major cities in the world to almost run out of water. So this has been linked to the expansion of the Hadley cell and climate change, so this all ties together. So that's why climate predictability in this region is very important and well studied. So this dipole pattern that I mentioned, where we get an increased rainfall in the east and a decrease in the west, is kind of highlighted here. So there's a lot going on in this, but most of it is citation. So I'll do my best to just explain it. So summer rainfall is what we're looking at. So December, January, February is associated with an increase in Eastern South Africa, whereas Western South Africa is associated with winter rainfall. I looked at the winter rainfall in this model and it doesn't do a good job of capturing any, whether in the west or the east. So that's why I'm just going to continue to focus on December, January, February. And what's interesting is we get two very different mechanisms that explain what's happening on both sides of this country. And so we have in the eastern side, we have the rainfall related to the tropical and extratropical cloud bands and associated convection in this area, as well as the warm SSTs from the Agulhas current. And so the warm SSTs from the Agulhas current, you get an increase in the moisture content as well as the advection over land. And so that's why we're getting an increase in the rainfall. And so what causes this increase in SSTs could be a few things. One, previously it's been shown that ENSO has a direct link in relationship with the SSTs in the Agulhas current, or as shown in this study, the increase in the greenhouse gases. So this is all going to tie together with the increase that we see in the Eastern Basin. And then I want to note that El Nino is associated with drier conditions in this region and La Nina with wetter conditions. As we shift over to the western side, however, it's a completely different mechanism. The rainfall is associated with these cold fronts in the region, which are results from the cyclone formation in the South Atlantic. And so when you have the poleward shift of the Hadley cell, you also have the poleward shift of these cyclones in cold fronts. So it's pushing the low pressure systems away from South Africa, and instead you get high pressure systems forming over the western region, which suppresses the rainfall in this area. So that shows that the Hadley cell is going to play a really large role here. But with the ozone recovery and the equatorward shift, the opposite's going to happen. We're going to have those low pressure systems shift back over to Western South Africa and an increased rainfall. And so again, this ties into the southern annual mode now, with the positive phase of the southern annual mode having positive anomalies of sea level pressure over South Africa. So you get this increased pressure over South Africa, which then suppresses the rainfall in this area. And then when it's in its negative phase, you get these low pressure systems forming in the region, which results in an increased rainfall. So the southern annual mode in its positive phase is related to a decrease in rainfall, and in its negative phase is results in an increase in the precipitation in this area. Another driver behind the rainfall in this area is the ENSO, the sea surface temperature anomalies, and Agulhas leakage. So that's something that I'll mention and talk about in a second as well. So I just want to zoom in essentially on what I showed before with the convective precipitation over South Africa, and you can see this clear increase in the Eastern Basin and this decrease in the Western Basin. So EB is going to be Eastern box, WB Western box in purple and in orange. And so this increase is shown with the ozone recovery minus the ozone depletion. So we're getting something that's driving this change, where you get an increase in the Eastern box and a decrease in the West. And this is also seen in the post-ozone recovery minus ozone recovery, with the Eastern box intensifying in its precipitation, likely as a result of the increased sea surface temperatures in this area. I don't show the figure, but if I were to zoom in on the same region for sea surface temperatures, you can see a very strong increase in the Agulhas region that you don't see elsewhere in this region. So it's likely linked to the sea surface temperatures seen here. So I just take the mean over these boxes. And so we have the Eastern box time series here and the Western box on the bottom. And you can just see the overall magnitude is larger, between 4 to 5 millimeters a day and 2 to 3 millimeters a day for the Western box. So you're getting more rainfall in the East. And so since we expect the rainfall in the East to be attributed to sea surface temperatures, and there's a consistent warming of sea surface temperatures throughout all the RCPs, we're going to expect a continued positive trend throughout all these time periods. And so we can see that there's an increase in the ozone depletion time period, and then a continued increase in the ozone recovery time period. But then as we go to the post-ozone recovery, where we have a decrease in the overall change of sea surface temperatures, we get a kind of stabilization of RCP 4.5 and 2.6 in the green and blue. But looking again, starting around 2060 for RCP 8.5, where we have our highest emissions and biggest increase in sea surface temperatures, we get a really large increase in the precipitation in this box as well. Shifting back down towards the western box, so again, this is going to be related to the Hadley cell suppression of rainfall now, with the shifting of low pressure systems off the coast of Africa. And so we have a decrease in the precipitation here and into the ozone recovery time period. But what's interesting is as we go into the post-ozone recovery time period, the RCP 2.6 changes sign. And so we get an increase in the precipitation now. And so that's likely related to the Hadley cell shifting towards the equator. But it almost looks like now as there's a lag that you're seeing. So we have the ocean feeding, or the atmosphere affecting the oceans, and the ocean feeding back onto the atmosphere. So there's a bit of a lag for us to see this signal. And then you can see as well in RCP 4.5, a weakening of the trend. But for 8.5, there is a continued decrease, likely associated with the continued poleward trend seen in the Hadley cell there. So what we want to look at next is the Agulhas current and the Agulhas leakage, since these are related to the precipitation in the area. So how I calculate the transport of the Agulhas current is simply just a cross-sectional transport across 34 south using the velocities. As for the Agulhas leakage, it's calculated offline using a Lagrangian particle tracking tool and the horizontal velocities from the model. And so how we do it is each particle is assigned a volume transport that is equal to the initial release velocity multiplied by the grid cell size. And then any particle that leaks, we basically take a sum of them at each monthly period, as long as their initial transport is southward. So I don't want to go too much in depth in this, but this is the Lagrangian tracking tool used. It's called Parcels. It was by Lange and Van Sabeel in 2017. I used it in my first paper as well. It's offline Python Lagrangian tracking tool and uses linear and nearest neighbor interpolation, and particles are advected using the RK4 scheme. So this is an example of how we release each cross-section of particles. And so you can see this is a cross-section of the Agulhas current at 34 south, where we see particles in each grid point. And then we assign it a transport, which you can see the highest transport is 0.4 sphere drops. And that's just, like I said, the initial velocity times the grid cell size. And so we release this cross-section of particles monthly from 1960 to 2100. We start in 1960, that way by 1970, we at least have particles in circulation and we can get the leakage calculated from then. And then particles are considered if they cross the Good Hope line an odd number of times and its initial transport is southward. So any particle that has a positive velocity here, we don't consider, we only take the negative velocities. And then the Good Hope line is defined in previous literature, so we just continue using that definition of leakage. So on the top, we have the Agulhas current transport, and on the bottom, we have Agulhas leakage. And so I take the annual transport for the Agulhas leakage because I get a strange seasonality in the leakage transport as a result of calculating the particles offline. So to get rid of that, I just take the annual. So that's the only one I'm looking at, an annual transport instead of the December, January, February. So beginning with the Agulhas current transport, I get a mean of about 65 sphere drops for the ozone depletion time period. And observed estimates show that the transport is 77 sphere drops. So we're not off by much. It's a pretty good estimate for a low resolution model. And then now in terms of the trend, you can see that there's a very clear decrease in the Agulhas current seen across all RCPs. And so you get a weakening of the trend around this time period, again, 2060 for RCP 2.6 and 4.5, where it starts to slow down a little bit, the decrease. But in 8.5, it's a really strong decrease from about 65 sphere drops to 55. So over this 130-year period, we have about a 10 sphere drop decrease. So initially, I wanted to know why this was happening, and my first thought was the wind stress. But after looking at the wind stress curl, the wind stress as a function of latitude, time, RCPs, there's no differences across each scenario with the wind stress or wind stress curl. So something else must be driving it, which I'll get to in a second. And then for the Agulhas leakage now, focusing on the ozone depletion time period, we get a mean of about 36 sphere drops, which is a better estimate from a study where they use the same model, same low resolution, where they get 43 sphere drops. So we have a little bit of a better estimate, but still far from the observed estimate of 21 sphere drops. And so we get this very sharp increase from 1970 to about 2015, 2020. And so this has been shown in literature where with an increase the increase in anthropogenic climate change resulting in an increase in leakage as well. But after this time period, it's kind of hard to say anything definitive about each RCP. You get kind of a stabilization between each one, or kind of a negative trend shown, but it's not that strong. So something after this time period is causing these to stop increasing. So it could be a long response to the ozone recovery, but there's not any data past this. So whether or not we'd see any changes past 2100, I don't know. And so this goes back to the change that I'm seeing in the Agulhas current. And so I want to know what was causing this decrease in the transport. And so what I looked at now is the transport cross section of the ozone recovery minus ozone depletion, post-ozone recovery minus ozone recovery, and then RCP 2.6, 4.5, 8.5. So set up similarly to what we've seen before. And so you can see they're very small changes, but you can see that there's an increase in the transport a little bit at the top in the upper 100 meters, but you get this decrease in transport from 500 to 1500 meters that's shown in the ozone recovery minus ozone depletion time period. And then as we go post-ozone recovery minus ozone recovery, you can see that we have back to an increase at deeper depths, so down to about 700 meters, and a weakening of this decrease in the middle. But then looking at 8.5, we get a really strong increase at the surface, the upper 100 meters, and then a very strong decrease from 500 to 1500 meters. So it's almost like we're getting a speed up at the top and a slowdown at the bottom in this scenario at the intermediate depth. So what's causing this slowdown? I'm not sure. And so that's something that I still have to figure out. The only thing I can think of is if the increase in sea surface temperatures are somehow playing a role here. So if we're getting these warmer waters at the top and colder waters in the intermediate depths, that there's some sort of slowdown and an issue with the stratification, or if it's just something wrong with the model. And so that's something that I'd see after looking at the high resolution runs. I'm tempted to think it's more to do with the sea surface temperatures, just because at the end of the transport for the Agulhas current in RCP 2.6, you can see that it begins to go back to an increase, suggesting that maybe the cooling off of the sea surface temperatures is playing a role here and here as well. But yeah, that's something I still have to figure out. And so I want to look at the Agulhas current versus Agulhas leakage relationship. And so Van Stabile in 2009 showed that there was a negative relationship. So an increase in the current transport resulted in a decrease in the leakage and vice versa. And so he finds a correlation coefficient of negative 0.67. And I find negative 0.76, negative 0.78, and negative 0.75 for my time series. But what is interesting to note is these black dots, the historical, I get a correlation of negative 0.92. So it's really strongly correlated there. So an increase in leakage is resulting in or an increase in the current is resulting in a decrease in the leakage and vice versa. So this is my correlation map. So I just want to explain everything very carefully. We have the variables considered throughout the talk so far: the radiative forcing, CO2, ozone, westerly jet strength, westerly jet latitude, the Hadley cell. The eastern box rain and the western box rainfall, Agulhas current and Agulhas leakage. And then in each box, we have 3 different correlations plotted. So it's the RCP 2.6, 4.5, and 8.5. So this allows us to compare everything together. And then places where you see the white, it wasn't significant. So for the most part, most of these variables are significantly related to each other. But what sticks out the most is this ozone variable. There's not a lot of correlation, and if it is, it's not telling a good story, which doesn't surprise me because most of the correlation we're going to see with the ozone, we're going to get from those maps. We're not going to see it in the entire time series. We'd see it in the maps as well as just the ozone recovery time period. And then I also want to say that the radiative forcing and CO2 are basically the same variable, so we're getting the same sort of trend here. And then some places that we get really strong correlations are the radiative forcing with the eastern box, western box, Agulhas current, and Agulhas leakage, the Agulhas current with the eastern box, and Agulhas leakage with the Agulhas current. And so we're getting really strong correlations actually throughout this map, and we find that a lot of these variables are closely related, which is a good thing. But yeah, so that shows and then places where we see differences across RCPs are with the westerly jet. You can see here as it slowly increases as we change emissions, and the Hadley cell suggesting that the emissions from 8.5 result in the highest correlation. So I also created some linear regression maps. I don't want to get into those right now, but there was like 12 of them, so I'm only going to summarize them. So we linear regress the eastern box, the western box, the Agulhas current, and Agulhas leakage with sea level pressure, sea surface temperature, latent heat, and convective precipitation. And so for the eastern box, we find an increase in the precipitation associated with a sea level pressure decrease, sea surface temperature and latent heat increase, and strong equatorial rainfall. For the western box, we get the opposite trends of the eastern box. So an increased rainfall in western Brazil and the Atlantic is associated with an increase in the western, and vice versa. What is interesting to note about the western box precip is that if I detrend the data and then plot it, almost all of the relationships disappear. And so that's suggesting that this is really forced by the external forcing signal here. For Agulhas current, we get an increase in transport means less rainfall, cooler SSTs, drier El Nino-like conditions in the eastern basin, and the opposite, a decrease in transport as we've seen in this study means more rainfall and higher SSTs and wetter La Nina-like conditions in the eastern basin. As for the Agulhas leakage, we get the opposite trends of the Agulhas current, as well as an increase in transport resulting in warmer SSTs, which makes sense. The more Agulhas leakage you have, the warmer, saltier waters from the Agulhas are entering that region. So to conclude this part, we find a weakening or reversal of the ozone depletion trends as the ozone recovers. So we showed that the westerly jet, the Hadley cell, sea surface temperatures, and precip all change or weaken as we go into the ozone recovery time period. How these trends continue depends heavily on the greenhouse gas emissions, which is why we consider the post-ozone recovery time period. And you can see that in the RCP 2.6, the ozone is dominant and you can have a continued ozone recovery trends. And then in 8.5, the greenhouse gases are dominant and you have continued ozone depletion trends. We also find that dipole pattern over South Africa with the east-west contrast with the increase in the eastern basin over South Africa directly related to the SSTs and the Agulhas current in that region. And then a decrease in the convective precipitation in the western box, a result of the Hadley cell expansion and poleward shift of the storm tracks, and is related to the external forcings. So what's next? 2 questions. How will these results change in a high resolution model? And what has the greater impact on the Southern Hemisphere climate system, the ozone or the greenhouse gases? So that's what we want to answer in this next chapter. So some high resolution advantages that I'm sure everyone's aware of, but just want to reiterate, they're eddy resolving high resolution models, and that's going to be important for both the ocean and the atmosphere. With the ocean, eddies are important as they transport heat and nutrients. And then in the atmosphere, as shown in the South African study, you can see that cyclones are responsible for rainfall over land. So that's something that I'm hoping will get better resolved as we look at the high resolution model. We can get better estimates of transport within the ocean. My Agulhas leakage transport is definitely higher than most low resolution or high resolution estimates tend to be, as well as better western boundary currents. So I think we're going to resolve the western boundary currents a lot better in the high resolution and get a better estimate of transport. And resolve high impact weather events in the atmosphere. Most low resolution models show hurricanes are just weak low pressure systems or don't even resolve severe thunderstorms, which I think is what's happening in the winter time there over South Africa. So the high resolution one should do a better job of that, as well as large scale climate patterns that are affected by smaller mesoscale features. Those are going to be resolved. So that means mountains that block precipitation or the blocking and dragging associated with mountains are going to be better resolved in high resolution models. And so what we also want to consider now is the ozone versus greenhouse gases prescribed independently. And so Pavani et al. Was one of the first to do it. With his 2010 study, he compares the ozone depletion with the greenhouse gases. So which one has a stronger impact on the atmospheric circulation? And he finds that the ozone depletion is 2 to 3 times stronger than the greenhouse gas forcings in an atmospheric model. And then in this study here shown, he looks at the ozone recovery and greenhouse gases to see which one has a larger impact. So in the middle, we have the zonal wind, and the ozone has a negative trend on the wind, and the greenhouse gas has a positive trend. But the overall trend is negative, suggesting that the ozone plays a larger role here. And so that's going to be the basis for our next study. And so how we're going to do this, we have 6 different simulations that we're going to consider. So 3 of them are low resolution at 1 degree and 3 are high resolution at 1/10 degree, but they are identical otherwise. So it's going to be low resolution versus high resolution. That's going to help show us the differences that we see there. And then we look at the historical CO2 versus year 2000 CO2. And so that's going to be the differences for the emissions with RC08 and RC20 having 2000, so that's the higher CO2 emissions, then RC07, which is the historical. As for the ozone, we have 2 simulations of ozone depletion, so year 2000 ozone levels, and then 1 simulation where we have ozone recovery, so year 1995 ozone. So we can compare the historical CO2 with year 2000 CO2 and the ozone recovery year 1995 03 with year 2000 03. And so the ones in red are runs that Ben and I have been working on. So I finished the low resolution runs and Ben is still working on the high resolution, but right now we only have 10 years of data, but it's still running. So I'm hoping to get a lot more over the next few months. So here you can just see the differences between the low resolution and the high resolution. The overall pattern is the same, but the details and the mesoscale features are clearly resolved in the high resolution. So we have sea surface height on top and surface temperature on the bottom. And so you can see that they're a lot, the mesoscale features are a lot more detailed in the high resolution. It's kind of like wearing your glasses and not wearing your glasses is how I look at it. But the overall patterns is the same, but how they resolve the features is going to be interesting. And so this is showing the difference in forcing that we are going to be using. And so this is the stratospheric ozone over Antarctica. So our ozone recovery is in blue, and these are the new runs that Ben and I are running, so RC20. And then the ozone depletion is shown in red, RC07, 08, those are already finished. And then the historical CO2 is shown here. So it's a lot weaker than the 2000 level emissions that we see in RC20 and RC08, and RC07 is the historical. So we have our control experiment being RC08, and the differences seen between those are going to tell us which is more important, the ozone or the CO2. And so I just want to start by showing that I don't have a lot of results yet on this, but just one is the sea surface temperatures. And so the top, we have the greenhouse gases, and the bottom is the ozone recovery. I don't have the low res done yet because I still have to regrid them. But you can see that there's an overall warming trend in the greenhouse gases, whereas we find a cooling trend in the ozone recovery, and that the ozone recovery trend is about 3 times larger than what we see for the greenhouse gases. So for sea surface temperature, it looks like the ozone recovery is going to be dominant in the high resolution run. And then we look at convective precipitation. And so this one has a lot of information, so I don't want to go too much in detail yet because I haven't fully understood it, but we have the low resolution on the left, the high resolution on the right, the greenhouse gases on the top, and the ozone recovery on the bottom. And so you can see in the low resolution, we get a really strong increase in rainfall pretty much globally. And it's a really large increase of 5 millimeters per day. But then if we look at the high resolution, you're getting a lot more details, and it's a small signal, 0.6 compared to the 5. So we're getting a big difference between the high resolution and low resolution in the greenhouse gases simulation. And then the same is true for the ozone recovery situation between low resolution and high. You can see it's a lot more detailed, specifically around the equator. We get this increased rainfall in the high resolution, but over here it's a decreased rainfall. So they almost look inverse of each other. So that's something that we're going to have to look at a little bit more. And it could just be because I only have 10 years worth of data for the high resolution case, and maybe later on we're going to see more of a signal that's matching the low resolution. And then comparing greenhouse gas signal to the ozone, you can see that there's a bit of a difference between the two in the low res, with there being less increase in the ozone recovery and more global increase in the greenhouse gas situation. And then actually kind of a similar trend between the greenhouse gases and ozone for the high resolution. So I imagine that this one's going to change more as we get more data for it. So what's next? Basically to redo everything that I've done for that first study with the high res and low resolution model. So do we see similar trends for the greenhouse gases and ozone recovery as we did for the westerly jet, Hadley cell, and things like that between low resolution, high resolution, and between isolating the trends? And then Ben and I would like to look more at the relationship of all the western boundary currents in the Southern Hemisphere with continental rainfall. And so we got this signal that I mentioned a couple times over South America as well as Australia. So we want to take the North Brazil current and the Brazil current and look at the relationship with South American rainfall. Again, Agulhas current with South Africa and the East Australian current with Australia. Okay, any questions?
Thank you. That was such a great presentation. If I saw a couple questions in the chat, but if anyone else has questions, we'd love for you to unmute yourself and show your photos. That way you can ask the question. Sanki, are you there? Okay, Mary Beth, do you want to go ahead?
Oh wait, Sanki just wrote back. Why don't Houraa can
we just read it from the chat? Okay, so.
Yeah, we can repeat it. So do you think that different Hadley circulation changes you see from the 3 RC? Oh, there you are. Would you like to ask the question yourself? We can't hear you.
I can just read it if you like, or just answer it since everyone's seeing the question, right?
Just since it's being recorded, I didn't know.
Should I just answer it? Okay, so they ask, do you think the different Hadley circulation changes you see from the 3 RCP scenarios are strongly linked to the ozone recovery? Unless you perform additional experiments with fixed ozone, it'll be hard to make that link. And that is true, which is why the first thing I state when we're talking about the different RCPs, I say it's going to be that's how we're going to extract the ozone signal, just because that's how they've done it in previous literature. When you have the greenhouse gases and ozone changing simultaneously, it's going to be harder to extract which one's related to which leads us to the next question that I proposed at the end of showing them independently. And then from there, we're going to be able to tell, okay, this one has the extreme ozone recovery, and this one's extreme ozone depletion. So any changes we see there, because they have the same CO2 emissions, is going to be related to the ozone. But those aren't the most realistic scenarios. The most realistic ones are when you have the emissions changing with the ozone at the same time, which are the CMIP ones. And then they ask, why am I looking at the December, January, February trend and not in the other seasons? And that's what I mentioned at the beginning, with the ozone being, the stratospheric cooling and the ozone being related to the September, October, November time period. That's when it's strongest. And then previous literature that does look at seasonality has shown that these shifts in the poleward shifts seen in the Hadley cell, westerly jet, and everything else are the strongest in December, January, February. So because other studies have looked at seasonality and I'm looking at the direct effect of the ozone, I just skipped ahead to seasonality and looked straight at December, January, February. Okay. Mary Beth?
Great presentation, Houraa. I was wondering about for your RCP output, especially the time series output, if or what type of error analysis you did. So I know that there's like inherent probability within the RCP scenarios that you choose. And so are you just using that, or are you doing error calculations on top of that? And is there overlap with the different RCPs when you do the error bars?
So I actually didn't do any error calculations on them, but what I took was each of the ensemble members. So the 5 ensemble member means, just to kind of get like to remove that interannual variability or some of like the errors you might see from one or the other, to kind of hope it converges on one sort of trend. But I didn't do any error calculations myself.
Gotcha. Okay, thanks.
Mm-hmm.
Does anyone else have any questions? Okay. If not, we can all give another round of applause to Houraa, at least virtually.
Thank you.
For a great
Thank you
presentation.
everyone for attending.
Okay, thank you.